Ever found yourself needing two functions that do nearly the same thing, but for different types of input? Or maybe you've run into a strange error where a variable just disappears when you leave a code block. These aren't random, they're part of how C++ handles function overloading in scope. In today's video, we're unlocking two essential tools that help you write cleaner, smarter, and more flexible code. First, you'll learn how to use the same function name for different purposes, depending on the input. And then, we'll uncover how scope defines where your variables live, when they die, and why some variables are visible while others are not. By the end of this video, you'll be able to create multiple versions of a function using overloading. Understand how C++ chooses which one to run. Master variable scope so you can avoid frustrating bugs. And write code that behaves exactly the way you expect. Let's dive in, starting with function overloading. Function overloading is a powerful feature in C++ that lets you define multiple functions with the same name, as long as they have different parameter types or counts. Think of it like this: you have one action, say, add, but that action can handle different types of input. You might want to add two integers, two floating point numbers, or even two strings. Instead of creating separate function names like add integers, add floats, or add strings, you simply write one function name, add, and define it differently for each case. Let's look at an example: int add, int a, int b, return a plus b. Double add, double x, double y. Return x plus y. Here, both functions are called add, but the first one works with integers, and the second with doubles. When you call add, 3, 4, C++ automatically uses the integer version. When you call add, 3.2, 4.8, it switches to the double version. This makes your code simpler, easier to read, and easier to maintain. And the best part? You don't have to remember multiple function names for similar tasks, just call add, and let the compiler handle the rest. Function overloading gives your code flexibility, while keeping it organized and intuitive. So why should we even bother with function overloading? Why not just create different function names for each version? Well, imagine you're building a calculator app. You want to create functions for adding, subtracting, and multiplying values. But your users might input integers, doubles, or even characters. Without overloading, you'd need something like add int, add double, add char, and so on for every operation, and that gets messy fast. Overloading solves this problem by letting you use one clean, consistent name, like add, and simply change what parameters it accepts. It improves readability, because your code speaks naturally: add, 3, 5, add, 2.3, 7.1, even though those two lines do different things, they're easy to understand at a glance. It also improves reusability, because you don't have to copy and paste logic into separate functions. Instead, you write targeted versions of one function, optimized for different data types. And most importantly, it reduces naming clutter. You focus on the logic, not on inventing a new name for every variant of a task. So whether you're working on mathematical functions, print utilities, or input handlers, function overloading makes your code simpler, smarter, and more scalable. Function overloading sounds powerful, but like every tool in C++, it comes with a few important rules. Let's break them down so you don't run into strange errors or bugs. Rule 1: functions must differ in the number or types of parameters. This is the core of overloading. You can write multiple versions of a function, as long as their parameter lists are different. For example, void print, int x, void print, double y, void print, string message. This is perfectly valid. The function name print stays the same, but each version handles a different type of input. Rule 2: return type alone does not count. You might think you can overload a function by just changing the return type. But C++ doesn't allow this, because return type is not considered during overload resolution. For example, int get, double get, error. Same parameter list, only return type differs. Even though the return types are different, the compiler won't know which one to call, especially if you don't use the return value. That's why return type alone isn't enough. Rule 3, be careful with default arguments, they can cause conflicts. Default parameters can make overloads ambiguous if you're not cautious. For example, void show, int x, int y equals 0, void show, int x, this is ambiguous. If you call show, 5, which version should the compiler choose? It can't tell, and you'll get a compilation error. So if you're using default parameters, make sure they don't overlap with your overloads. To recap, you can overload by changing number or type of parameters. You can't overload based only on return type. And you need to avoid conflicts with default arguments. These rules help keep your overloaded functions clear, consistent, and compiler-friendly. Alright, time to test your understanding with a quick mini quiz. I'll show you a few pairs of overloaded functions. Your job. Decide if each pair is valid or invalid in C++. Let's go. A. Void log, int x, void log, float y, same function name, different parameter types. Valid or invalid? B. Int get, double get, same name, same parameters, only the return type is different. Valid or invalid? C. Void show, int x, int y equals 0, void show, int x, default argument creates overlap between the two functions. Valid or invalid? Take a moment, pause if you need to, and when you're ready, let's reveal the answers. Let's go over the answers and make sure everything's crystal clear. A is valid. Void log, int x. Void log, float y, these two functions have the same name but different parameter types, so they're valid overloads. When you pass an int, the first one is used. When you pass a float, the second one is used. No confusion for the compiler. B is invalid. Int get. Double get, these have identical parameter lists, and only differ in return type, but C++ doesn't allow that. Why? Because when you call get, the compiler can't figure out which version you meant, especially if you ignore the return value. So this will result in a compilation error. C is invalid. Void show, int x, int y equals 0. Void show, int x, this one's a bit tricky. Even though the parameter lists look different, the default value in the first function makes them effectively the same when you call show, 5. The compiler sees both functions as possible matches, and throws an error due to ambiguity. So remember, overloading works when functions differ in type or number of parameters, but it fails when differences are only in return type or default values create confusion. Nice job if you got them all right. Now let's move on to an equally important topic, scope. Now that you've mastered function overloading, let's switch gears and talk about another fundamental concept in C++, scope. Scope simply refers to where in your code a variable exists and can be accessed. It's like a container that defines the lifetime and visibility of variables. Think about it this way, if you declare a variable inside a function, it only exists inside that function. If you try to use it elsewhere, the compiler will complain, because that variable is out of scope. Here's a quick example, void greet. Int x equals 10. The variable x is only visible inside the greet function. Try to use it in main, or anywhere else, and you'll get an error. Understanding scope helps you avoid one of the most common beginner mistakes, referencing variables that don't exist in the current context. But there's more, scope isn't just about visibility. It also controls when a variable is created, and when it gets destroyed. So if you declare a variable inside a loop or an if block, it gets created each time that block runs, and vanishes as soon as the block ends. In the next part, we'll explore the different types of scope in C++, and how they affect your program's logic and memory. In C++, scope comes in several flavors, each one controlling how long a variable lives and where it can be accessed. Let's go through the three most common types you'll use. 1. Local scope. This is the most common, variables declared inside a function or block. They only exist while that function or block is running. Void say hello. String name equals Alice, local scope. Cout hi, name. Once say hello finishes, the variable name disappears, it's destroyed automatically. 2. Block scope. This applies to variables declared inside curly braces, like if, for, or while blocks. If, true. Int age equals 25, block scope. Cout age, error. Age doesn't exist here. Even though age is inside the same function, it was declared in a separate block. Once the block ends, the variable is gone. 3. Global scope. Variables declared outside of all functions live in the global scope. They're accessible anywhere in the file, unless shadowed. Int counter equals 0, global scope. Void increment. Counter plus plus. Global variables stay alive throughout the program's entire execution. But be careful, overusing them can make your code harder to debug. To summarize, local scope, inside functions. Block scope, inside loops or conditionals. Global scope, outside everything. Knowing when and where your variables exist helps you write safer, cleaner code, and avoid bugs like using uninitialized or destroyed variables. Next up, we'll talk about something sneaky that often trips up beginners, variable shadowing. Now let's explore a tricky, and sometimes dangerous, concept in C++, variable shadowing. Shadowing happens when a local variable has the same name as a global or outer variable. When that happens, the local version hides or shadows the outer one, making it temporarily invisible inside that block. Let's see an example. Int value equals 100, global variable. Void display. Int value equals 50, shadows the global variable. Cout value, outputs 50. Even though we declared value equals 100 globally, the local variable value equals 50 inside display, takes over, and hides the global one within that scope. So when you call display, it prints 50, not 100. This might seem harmless, but it can lead to subtle bugs. If you're not aware that a variable is being shadowed, you might spend hours trying to figure out why your code isn't behaving as expected. Here's another example with nested blocks. Void test. Int number equals 10. Int number equals 20, shadows the outer number. Cout number, prints 20. Cout number, prints 10. Inside the inner block, number is 20. Outside, it goes back to 10. Each variable is valid only in its own scope, even if the names are the same. So the golden rule: avoid reusing variable names in different scopes unless you really need to, and if you do, be clear about your intent. Up next, we'll bring everything together with a real coding example using function overloading and scope at the same time. Now let's bring it all together in one simple live coding example, where we combine both function overloading and variable scope. We're going to write a program that defines multiple versions of a function called log, and then explore how variables behave in different scopes inside that program. Here's the code: include iostream. Using namespace std, void log, int number. Cout logging integer, number yendl. Void log, string message. Cout logging message, message yendl. Int main. Int value equals 10, string text equals hello world, log, value, calls the int version. Log, text, calls the string version. If, true. Int value equals 99, shadows outer value. Log, value, still calls the int version, but prints 99. Log, value, back to outer value, prints 10. Return 0. Let's walk through what's happening here. First, we define two overloaded versions of log, one that accepts an int, and one that accepts a string. C++ automatically chooses the correct version based on the argument type. Then in main, we declare a variable value equals 10 and a string text equals hello world. We call log, value, which uses the integer version, and log, text, which uses the string version. Inside the if block, we declare a new variable value equals 99. This shadows the outer value. So when we call log value inside the block, it logs 99. But once we exit the block, the inner value disappears, and calling log value again goes back to using the original 10. This example shows how overloading lets you reuse function names, and how scope affects which variables your code actually uses. Together, these features make your programs more flexible, but they also require you to be aware of what's happening behind the scenes. Awesome work, you've just explored two key concepts that every C++ developer must master: function overloading, so you can write cleaner, more flexible functions. Scope, so you know exactly where your variables live, and where they don't. These features aren't just academic, they're essential for writing real-world, professional-level code. Understanding how to reuse function names and control variable lifetime gives you more control, more clarity, and fewer bugs. Now you're ready to go even further. In the next video, we'll take a big step forward, into the world of arrays in C++. You'll learn how to store multiple values in a single variable, how to loop through them, and how arrays work under the hood. So don't stop now, keep building, keep coding, and as always, like, subscribe, and share this with someone who's learning C++. See you in the next one.